one and go. Logarithms. What are they? Well, we're going to try to answer that today, but for right now, they're another transcendental function. Exponentials are transcendentals. Logarithms are transcendentals. They're inverses of exponential functions, but only when functions have common bases. We'll get back to that with some properties we're going to see today. Does anybody know the name of that one or that one?
Logarithms.
Logarithms. Huh? Natural? Which one's natural? The one with an N that's after the L? That's weird. Because his name is not logarithm natural, but natural logarithm. Maybe that's why the L is before the N. Maybe it came from a different language. Interesting. ln is the natural log, or the natural logarithm. And why is he called that? Well, because even though you don't see it, and actually in either of these, you don't see their bases, they're kind of hidden because they're defined to be somebody. But natural log is log base, even though you'll never see it, e of x. And put the little e in quotes because technically it's not supposed to be there. We write ln instead of writing log base e. But for some of you, when you see an ln, it might be easier to think log base e just to remind yourself. He's just a logarithm with a special base. And what did we learn yesterday about the name of this guy? The natural number. Oh, the natural log has the base of a natural number. That kind of makes sense. And why is it called natural? Because it happens in nature. Coming back to him. What's his name? Kind of. It's kind of like standard. It's another name for it, sort of. Nothing? Trying to think of one. Starts with a C.
Common.
There you go. Try to think of something that would rhyme with. Common is the common log. And shorten logarithm to be log. The common log. Does anybody know what the common log has as its base?
10.
Yes. Why would a common log have a base of 10? Or why would a log with a base of 10 be called a common log? What's our entire numbering system based upon? Yep. Unless you're doing modular math, which we're not, so that's okay. Or binary code, which we're also not. There are other ways besides base 10 or number system based on 10, but that's not what we're doing. That's why some people think that we should totally convert to the metric system because it's based on tens. But I'm not sure if that'll ever happen because Americans are a little too proud. So anyway. Is there anything else we should write on this page? Now let's keep going. Wait, hold on. What's true about your calculator? Are there any special logarithmic buttons?
Yes.
Which ones?
Log and log.
Hey, so when you see the log button, does it mean any log?
No.
What's it mean?
Log.
Just log 10. And if you see ln, does it mean any, well, first of all, it is a log, because that's kind of hard to see, but second of all, it's a log with what base?
E.
E. Now, real quick, is there anything else in your calculator, or anywhere else in your calculator, where you can deal with logs of different bases?
Yeah.
Little cheaters, where is it?
Math?
Math?
Yeah, math. Down all the way to log base.
Yeah, math, scroll down to log base. Math, scroll down to log base. Now, there's a slight dilemma. If your calculator has a yellow button on it somewhere, you're not going to have this. And sadly, you can't have this. Sorry. Does anybody else have a calculator with the big yellow button for the second? Yeah. So then, your guys' it's not going to be able to work. And here's the reason why. Basically, when they updated the calculator, they updated the programming language. That one can do it, and that one can't. But it's okay. We have a formula for those who can't. But there is that log base that lets you do a log of any base. We'll come back to it soon. Okay. Let's talk about the parent. Well, no. Parent function is graphing. Let's not do that first. Let's just talk about a general, not a common. That wouldn't work in this case. Too many math words have, or too many English words have mathematical meanings. You have to be careful. But the standard form. The standard form of just a general basic log. Once again, I like to write log base b of x just to remind me e is the base, but that's okay. We can do log base a. Hey, nice shirt.
Is it somewhere?
Oh, where's the log base A of x. Hey, I keep saying it. Have you guys heard it? Who's A then? Exponentials have a base 2 to the power of, logs have a base, log base 2. X, he's called the argument. We'll talk about him in a second. And y, well, y is just the logarithm, but let me give you maybe another way of thinking about that logarithm. Here's where it gets a little weird. Logarithms, I don't know if I can necessarily say they were designed or developed to, but they do describe powers. Logarithms help us zero in on powers. Another way of saying it is each logarithm represents a power, which once again might be a little weird. Let me just for 1 second take a peek at where I'm going. Okay, let's come back. Go forward in your notes. Logarithms can be seen as powers. And here's the reason why. There's actually a spiffy way of transforming or seeing how to go between logarithmic. We could say logarithmic form, which is the form that has a logarithm. Logarithmic to exponential and exponential to logarithmic. I'm sure you guys have seen this before. Doesn't mean you remember it, but you've probably seen it. Our brains don't really work in logarithms very often. They work more in exponentials because you guys have been dealing with those for longer. Logarithms are newer, so they're less familiar. And so I quickly demonstrate why I'm saying logarithms are powers, so why I'm saying this entire thing, or the y, is really just a power. If I had a log, y equals, let's just make a base. Let's not do common log or natural log. It's hard to know their base. Let's do log like base 7 maybe. 4, 7. Oh, there's a 4 down there. We'll do 7. Log base 7 of x. Okay, that's logarithmic form. 4k.
There's a log.
There's a log, yeah. That's all there is to it. But there is another way of writing this function. And the other way of writing this function says, log has a base and exponential functions have a base. We can say log base 7 corresponds to 7 as the base of an exponential, so a big 7. If y is the power, he's the power of the base. So 7 to the power of y equals, 7 to the power of y equals x. A silly way of remembering is keep the base and then go back and forth. So find the base, 7, go back and forth. 7 to the power of y equals x. But you can also memorize that y is a power. Or there is some math that we can do that kind of shows why this is true. But for right now, we're just saying, hey, you can go back and forth between exponential form and logarithmic form because they are related. Because they are related. We'll get back to that. For right now, we're starting off with evaluate. Do you guys remember in section 3.1 when it said evaluate this exponential function at x equals 3.1? What did we do? What do we do if it says evaluate?
Plug it in.
Plug it in, plug it in. How? We're not doing properties or anything crazy right now, so literally all we're doing is calculator. Can you figure out how to plug it in? Now, those of you that have the log base, you're spoiled rotten. Those of you that have the log base, you're spoiled rotten, because all you have to do for letter A is just plug in that math and then log base and just do log base 2 of 32 and see what that equals. And then for letter B, log base 4 of 2 and see what that equals. And if you guys have hit the log button very often, you're like, oh yeah, those are usually like exactly decimal things. So why don't you go plug it in and let's see what they are. Log base 2 of 32, what do you get?
5.
That's not a weird decimal. Huh. Wonder how that works. We'll get back to it in a second. But then go to the next one. Log base 4 of 2. Okay, this one's bound to be a weird decimal.
45.
1/2. It's a little nicer than maybe you expected. Unless you understand how logarithms work, then maybe it wasn't so surprising after all. But those of you who are like, I don't have a log base button, number 1, or number 2, if you're asked in homework to not use a calculator and still somehow change the base, we might need to use this formula. So for those of you that don't have a log base button, or in the olden days when calculators didn't have a log base button, you would have to use this if you were using your calculator to solve for any log besides the common log and the natural log. And there are some times in problems where it's going to be helpful to say, I don't like the base I have, and I'd rather have another one. And that's where this formula comes in. So for those of you, especially with the yellow button on your calculator, you're going to need this from the beginning of homework, kind of. And then the rest of you will need it whenever it starts talking about how to change a base. We can go from, how have we been writing it for the book? Log base A of x, is that right? But what if we don't like it? What if it's not working out with the stuff that we're trying to do? What if we'd much rather have a different base B? No big dealio. There's a formula that relates. Log base B of the argument over log base B of the old base. So, help those with the yellow button on their calculator just literally cannot support what's going on. Those of you guys with the snazzy newer calculators, the constant arm and legs, we want them to be able to keep their calculator, right? And just don't lose it, put your name on it, scratch it in something. But help us out. If they were trying to do the example, or the examples we were just talking about, what log base are they going to want to change it into? Log base 10, because there's a button for that, or they could also change it into what? ln, either one. So technically, just quick examples of what we could do, we could then say, like if we're trying to get to those easy buttons, we could just do log base 10 of x over log base 10 of a, or another way of saying it is, we could do ln of x over ln of a. To practical working out. Now guys, technically we could also, in this formula, we could go to log base 13, I'm just choosing another b. That one is 10, that one is e for ln. I could go to log base 13 of x over log base 13 of a, but is that going to help them any? No, they can't do log base 13 the same way they can't do log base 4 or log base 2. So if you guys want to check it real quick and make sure this is legal and this is safe, then we could go ahead and redo these two examples. And if we did redo them, another way of solving log base 2 of 32 would be, I'm going to say f of 32. Let's assume you can't just plug log base 2 of 32 into your calculator. We could do common log of 32 over common log of 2. That's how we work it out. Plug in a 32. We need to change the base to something easier, to a button that, especially in this context, the older calculators have. So if there's a 32 plugged in, using our formula, the 32 is the x, the 2 is the a, and so we say log, the new log, common log of the 32 over common log of the old base, which was 2. Or similarly, if we went down to this one, f of 2, we could say ln of what goes there, which is 2, over ln of the old base I didn't like 4. And if you guys plug and check, guess what ends up happening? He's 5, and he's 1/2. It doesn't matter what log you go into, it's going to equal as long as you use the change of base formula with the new log of the argument, whoever's there, and then the new log of the old base. And technically, if you talk to any calculus kid and you ask them, hey, which log is your favorite? What do you guys think they say?
Natural.
Natural. You might not know why though, because you're like, ugh, that's the ugliest one. That's the hardest one to remember. Like ln, what's going on? But they're gonna like ln the best because, long story short, his rules are easier. So hence why I'm trying to write ln's as often as I can, just to make sure you guys know he's just a log. All right, let's talk about some properties of logs. Let's talk about some properties of logs. Now, we didn't really talk about a lot of exponential properties. Maybe we should have. We kind of reviewed them in the sense of a power to a power you multiply. We kind of reviewed that yesterday. Like bases multiplied, you add the exponents. Like bases divided, you subtract the exponents. And as you guys are writing the logarithmic, let me write the exponential just for reference, just as an FYI. You don't have to write these in your notes per se. So we're going to talk about why and how do you write down the logarithmic and not the exponential. Now, just a few of you, if I had given you parts of these properties, just a few of you might have been able to answer them and say, oh yeah, any log of 1 is always 0, no big deal. Any log base A of A, oh yeah, it's 1, no big deal. Maybe some of you could even have remembered that logs and exponentials undo each other. Probably a lot of you could figure out the one-to-one property just from what we saw the one-to-one property as yesterday with exponentials. But I'm guessing most of us are like, yeah, I don't know these. Maybe I've seen them before, but logarithms, you just go back to the whole, I never liked them. I never could get them. Or I memorized them real quick and did okay on the test, and now I can't remember anything. But let me come back and ask you the exponential properties. We've talked about them a little bit. Let's just try to review them real quick. Like bases, what do you do with the powers? Add them. So a to the b times a to the c is a to the... What do we do when we have like bases being divided? Subtract what? Good. The exponents, right? Or the powers. We've reviewed this one kind of. A to the negative b. Who's that? Yeah, we throw him in the denominator because right now he's not in the denominator, so that's where he needs to go. And what do you do when you raise a power to a power? I'm guessing a lot more of you know these than you know those. Remind me, why is that true? Nobody likes logs. That's an excuse that everyone keeps using every year. I like them too, but most people don't. Number one. And number two, guys, why wouldn't you like logarithms as much as exponentials? If you had to choose one, you're like, give me these any day. Which one have you been learning longer? This one, all the way back to algebra 1, when you had like x squared over x to the 5th, and you had to like write out the little x's and be like, look, they cancel. And then you got 1 over x cubed and said, wait, they subtract. Anyway, you've been seeing exponential longer, so of course you're going to be more familiar with them, right? Anyway, let's come back to logs and try to get more familiar with them as well. Familiar new groups. Anyway. Remember just a second ago, I told you about how you can go from logarithmic form with your y equals to exponential form, a to the y equals x. I'm not sure if you need to write it again, but we just wrote that down just a second ago. You can go from logarithmic to exponential or backwards. They're trying to kind of show you where some of these properties come from, in that any log of 1 is always 0. That's true. Any log of 1 is always 0. But why? Well, because if you change it to exponential form, base to what is always 1? Well, base to what is always 1? Any number to what is always 1? 0. That's a defined value that you guys have hopefully been studying for quite a while now. 2 to the 0, 8 to the 0, pi to the 0, 100 to the 0, anything to the 0 except for 0. That's weird. Anything besides 0 to the 0 is 1. Now this one's a little bit trickier. Log base a of a. However, if we find some more properties of logs from next section, maybe you guys can remember that logarithms and exponentials, thinking about going back and forth. A to what power is going to be A? Like over here, A to what power is 1? A to the 0 power is 1. A to what power is A? Oh, just to the first power, no big deal. So we can say kind of, in a sense, whenever you see log base A of A, kind of like they cancel out and you just get whatever power is up there, which in this one we're going to learn a power property of logarithms that lets us pop the power down, and that will change or at least help us a little bit too. Number 3 is a big one. I need you guys, if you have a highlighter or something that helps you mark down what's most important. All of these properties are important. They're super, super helpful. But number 3 is especially helpful. It kind of comes from number 2. And it comes from the idea of how exponential and logarithmic functions are inverses. Exponential and logarithmic functions are inverses, so they undo each other. And what I mean by undo, what are some other common inverses? Oh, hey, square root squared. What happens? They undo each other, right? What happens with addition and subtraction? They undo each other, right? As long as it's of the same quantity. Powers and roots undo each other as long as they're the same index, or the same square root with the square, cube root with the cube, etc. Adding and subtracting undoes each other as long as it's the same value, plus 1, minus 1, plus 5, minus 5, etc. Logarithms and exponentials undo each other as long as they have the same base. And then the one-to-one property says, sweet, if the log base matches, then the arguments match, and I can just ignore the logarithms altogether. So then when we get down here to these examples, kiddos, and you see something like log base 11 of 11 to the 7. That doesn't match. But it kind of does, because it's not number 2 really, it's number 3. Log base, oh yeah, they match. 11 to the 11, so it's just going to equal 7. Just from the inverse property. The log base 11 undoes the 11 to the power of, and all you have is, well, the power, which is 7. But letter B, log base pi to the pi, or of pi, I should say. Log base pi of pi to the 1, what's that going to end up equaling? Just 1. So you can think of it as log base pi of pi to the 1. All of this cancels, the 1 is left, or you can actually, I guess, memorize number 2. Or think pi to the what power is pi? Oh, 1. Oh, see, that's just gross. We plug it in our calculator, right?
Oh.
Any log of any base of 1 is always equal to 3.2 to the what power is 1? 0. So if you can, if your mind doesn't think in logarithms, if you can think in exponentials, you can do things like 11 to the what is 11 to the 7. And maybe your 11 to the what is 11 to the 7 helps you say, oh, hey, yeah, the answer is 7. Or the unknown is 7. I put X to stand for the unknown. Or over here, if you didn't know, it could be changing. Pi to the X is equal to pi to the who? The 1. Oh, yeah, the answer must be 1. Or 3.2 to the I don't know who equals 1. Well, that must be 0. So there are different ways of writing to go back. So let's end with this example. Oh man, there's logarithms everywhere, but they're both common logs, and there's one on each side. There's a one-to-one property that says if the logs and the bases match. Maybe this one won't be our last one after all, because all we have to do is what? Oh. Say hey, they match. Sweet, 5x plus 1 must be 12 because logarithms are 1-to-1. Just like exponentials were 1-to-1, so we were able to say as long as they match completely, I can just take the power. Well, I can do that with logarithms too. So I get 5x equals 11. Okay, it's not pretty, but it's right. True? But let me show you another quick reason. Just because this other quick reason will help us when they maybe don't match. What's the understood base for all common logs? Okay, I'm going to write them in. I'm supposed to be there. I'm going to write them in so we can think about it. What property in your notes takes a logarithm, does something to it, or has an additional piece, and suddenly the logarithm is gone? What property has a logarithm on the left but doesn't have a logarithm on the right? Well, those has to be. Huh. Look, it has a log and then it doesn't have a log. It has a log and then it doesn't have a log. Now, I guess in some senses they all have logs and they don't because they're answering them. But number 3, the inverse, if his keyword for all inverses is undo, well, what do I want to undo over here? Undo the yucky logs we don't like. Well, how do we undo yucky logs? Do you know how when there's a square you can put a square root? Or when there's a square root you can put a square? Or when you have addition you can put subtraction. When you have multiplication you can put division. When you have a log base 10 you can put a 10 to the power of. So you can put whatever you do to one side, do to the other. Another way of looking at how this property, the one-to-one property, works is 10 to the power of log base 10. What happens? 5x plus 1. 10 to the power of log base 10. What happens? Just 12. So that might be a mathematical step as to how to get to 5x plus 1 equals 12 without just memorizing one-to-one property. But I just want to show you that quick little snippet. Oh, wait. Why did I say section 3.2 start? Because I've split section 3.2 into 2 pieces. So wait a minute, homework number 19, is that all of section 3.2?
No.
It's just section 3.2 part A.
Oh, that's like
So is it going to be the entire length of a normal homework? No. So what am I trying to keep you accountable on? Starting. So I gave you the first half of homework, and I said, hey, he's his own little homework assignment, and he's due Monday. You're welcome. Let me go ahead and pull it out. Get your spiral out. I'll let you write him down.
Wow.
Yeah, I know exactly how you guys operate if I don't make him a homework number. Mm-hmm.
Wow.
Wow. Tricky, tricky, tricky.
Well played.
Let me get you the homework assignment. We have enough time, but I think you guys should be able to write them down. Maybe not too much else. If you notice in your homework sheet, so we'll finish with 3.2 on Monday, and all of homework for 3.2 should be done by Tuesday. But we will quickly check homework number 19 on Monday. If you guys notice, maybe I also cut him down because he was just kind of brutal to have his one big assignment. So I'm keeping some of you accountable.